have a procedure, right? So working, so very good. Now, let's say you're trying to get enthalpy. Can you compute enthalpy? So if I give you this problem right now.
Oh, CPDT.
What?
CPDT.
Very good. All right, so it's equal to m dot Cp T1 minus D2A. And that's how you actually get your work. Oh, sorry. Yeah, we're gonna have another one. We're gonna have to. You remember what this looks like, so. Minus 2A. Efficiency for the system. So what do we get? We know T1. Let's list our unknowns. Yeah, we're not going to get to gas mixtures today. Just hoping to do that. What are our unknowns here? Do I know m dot? Yeah, because I'm the designer. CP, I already know it. So do I know T1? Yes, that's whatever condition I'm putting into my compressor. T2A is the one that I don't know. So that's the first unknown that comes across that I don't know. So we'll say, I'm a little bothered with this, I'm sorry. I'm just going to write it the other way. T2A minus T1 as work input. But it is correct. Just keep your conventions the same. Okay, let's keep it in the notes that way because I don't want people to get confused later on. We want the high temperature minus the lower temperature as long as you know what's in and what's out as work. Okay? But I think all of you understand it very well that we don't have to worry about it. Okay, so this is where we know T1, we know CP, we know m dot. What do we get as an output, as a unknown value is T2A. That's one unknown. What else do we don't know? The work in. I don't know how this compressor is going to perform yet. I know its efficiency, but I don't know what the work is. So work 2. Okay. How can I get that?
Compressor
Efficiency. Very good. So we already have the efficiency of the compressor is equal to, and we just already derived it, and we said it's the isentropic process relative to the actual. So it's H2S minus H1 over H2 actual minus H1. Well, I don't want to deal with entropy directly, enthalpy directly, so I could just take CP, and by CP, assuming it's constant, that's why assuming constant specific heat is always an easy thing because it cancels out. So what you end up with T2S minus T1 over T2A minus T1. So if I know my efficiency, right, and I know my T1 and I know my T1 here, and excuse me, I'm trying to find T2 actual and T isentropic. Do I have the T2 isentropic? Did you realize what your colleague said? Pressure difference. Where did that come from? We haven't seen it today. So isentropic relations, right? Where is it? Your tables that you used at the high speed area. But here we're going to use equations. Right here. Right. This is assuming what? Isentropic process. So meaning my T2 here is T2S. So I could just say, well, I know this, I know this. How do I get my T2S? So T2S is unknown. There's another third unknown. But how do I get it? I get it from, and I'm going to do it in red right here. This, we'll get it from 1 to 2S isentropic relations. And from there, it's T2S over P1 is equal to P2 over P1, and it's gamma minus 1 over 1, regular gamma. I know P1, and I know P2, and I know T1, and I know gamma as a designer. So therefore, I know all these values I could get T2S. Once I know T2S, I know this, I know this, I know this, I know this, I can get my T2A. Once I got my T2A, I go back and figure out the work. Straightforward? All right, so let's do the combustion chamber. Again, I keep calling it a combustion chamber, but in reality we're modeling it as a heat exchanger, but the principle is exactly the same. All we have to do later on is account for reacting mixtures and species and heat of formation. So that's the only difference. So what happens to the combustion chamber? If you apply the energy equation, which you have right here, well, I don't have work being done. It's a steady state process. So all I get is Q is equal to my amplitude. So if I list this same equation, 0 is equal to Q in, change the color, I guess. Plus m dot, what versus what? Where's my cycle? Right here. What versus what for heat exchanger? Very straightforward. H3 minus H2A. H3 minus H2A. All right, so I don't want to deal with enthalpies directly. I understand that I could say, well, Q in is equal to m dot Cp. See, conventions. So what happened there? So I followed what your colleague told me. But I have this Q in. Think of the energy equation. What did I end up doing here? Right here. Did I violate my signs? Right? Sum of m dot in minus m dot out. So your colleague automatically said 3 minus 2 actual, right? From the sign perspective, is that correct? Which is going to be higher?
3.
3 is going to be higher. So when I move this on the other side, I can put this as a minus and account for the fact that this is negative and know that this is my heat input, or I can just move it onto the other side and say it's the lower temperature versus higher temperature because it's heat into my system versus what's going to go out. So as keep the signs the same, you're okay. But based on my work in, heat is opposite to work. So it's supposed to be negative. Right? Because it's first law of thermal. Right? What did we say? We said total energy is equal to so if you keep work in as a negative, then you just have to put your heat sign. As long as you understand the sign convention, you should be okay. Question?
When we first started the problem, we were calculating work in, we did H1 minus H2A. Are we still keeping that convention, or are we now doing H2?
Well, that's what I was just pointing out, that your colleague mentioned H3 to minus 2A. If you want to keep the convention the same, the best way to do it is to say, no, it's actually MCP T3 minus T2A, but if I keep it that way, I'm going to move this and this. So if I go with what your colleague mentioned right here, what's going to happen is I'm going to move it on the other side. I'm going to say Q in is equal to m dot Cp T3 minus T2A. That's what I'm going to end up with. But that says that, no, this is actually work heat out. So this convention, although it's correct, given what we just did for the compressor, it's the wrong sign.
It's just confusing that don't you have two ways of putting it in the compressor, like two conventions? Going from H1 minus H2A, and then right below where you box it in, you have H2A minus T2A.
Yeah, but it depends on how you're seeing it as an input versus output.
I understand that, but that's
Okay.
two separate conventions right there that you said.
And that's what I'm saying. I don't want to keep it that way.
Okay. This is-
I'm saying, no, I don't want to do this. I want to do this. Because it's heat. Follow this equation, okay? That's the best way to do it. Just follow the same equation that you have here. If you keep that same equation the same, you don't have to worry about signs. So if you get confused what's in versus what's out, if you don't appreciate it, in a sense, follow the same exact convention. So how do we follow the same convention? Qn, I just listed it here, right? M dot of in, right? Minus my M dot out, okay? So that's the best way to handle it. So I don't want to do this one, but it's correct. It's just as long as you understand the signs. What's in versus what's out. All the differences is going to be negative. Just makes sense. Am I putting heat in or taking heat out of my system? That's all. So you're going to get the same exact answer. All right. So based on this, what do we know versus what we don't know? Well, I don't know my Q in. That's my fourth unknown. I'm trying to list all the unknowns here. These are unknowns. Do I know my T3? Yes, that's what I'm outlining as my combustor, or temperature, highest temperature that I have. Do I know my T2A? Well, I got it from the previous step, from my compressor. So I already know this, I know my M dot, I know my CP, I can get my Q. Okay? So moving on. Turbine. Same principle. 0 is equal to minus, I'm going to follow my sign convention, work in from the compressor versus the work out that I'm going to get, plus M dot H3 minus H4A. Well, what do I have here? I have work out is equal to minus W compressor in plus M dot, which is positive work, minus H4A. So let me pull up the diagram of the gas turbine engine and let's talk about it in terms of what's going in versus what goes out. Okay, so what do I have here? I have, we can see the equation and we can see the gas turbine. I have a compressor right here that I'm putting work into. Right, there's WC in. Where is this work in coming from? The turbine. So the turbine is actually producing, that's the useful work, it's producing work to drive the compressor, but it's also producing work that I can use for thrust or drive a fan or so forth. So this turbine is producing work in this direction and in this direction. Now, if I don't have this shaft, right, then when I expand my gas through my turbine, all the work is going towards work out. But since I have to propel that compressor, I have to take some of the work from the turbine to drive the compressor. So as a result of this, I have a negative work that is acting on my turbine. It's a loss. So this is my useful work. If I don't have compressor work, this is my useful work out of my turbine, which we just did when it was a separate component. In this system, no. I have a work that is actually being taken out of it. So that's where sign convention will play a big role. Now, let's say I decided, so this is the mistake that most will make in terms of sign. Here's where it's the issue. I'm going to write this in terms of M dot H2A minus H3. What happens there? Which one is higher, H3 or H2? H3. So what am I going to get for that value? A minus value. A minus value plus my compressor work. So now I over-predicted